Okay, I think we can get started for today. Are there any questions about the homework or any of the previous classes before we get to today's material? Yeah.
How do we hand the homework?
So for the homework, the written part, you can either hand in online on Blackboard or bring here. The code, please hand in online through Blackboard. And please check the course information handout, which has some pretty detailed instructions on what I want for the codes. We have to test everyone's code, so having it in a uniform format helps a lot. Any other questions?
So in problem 3, you say model the assembly of fragments. Are you trying to assemble them into a genome, or does assembly mean something else here?
Assembly would mean a genome, or at least a larger piece of sequence. So you're trying to assume all of the fragments came from a larger piece of DNA, and we want to know what the original piece of DNA is. Yeah, so the homework's due as of class time on Thursday. And one more announcement, or actually I guess a couple more. So for anyone who didn't see the email, we've now got at least a volunteer course TA, Greg Smith. So he'll be holding office hours 4 o'clock Wednesdays, so 4 to 5:30. That's at my lab, MI 654. And I guess, have you all got the link to the Box site if you want to access videos? Okay. All right, so I guess we can get going with today's material. So we're moving on with the topic of optimization, in particular continuous optimization. What I want to talk about today is what I describe as general continuous optimization or unconstrained optimization. And this is a problem in which we would assume in the general case we have some function, the function of a bunch of continuous, that is real valued variables. We would often represent that as a function of simply a vector of real values. And we're trying to find maxima or minima of this function as a function of the set of variables. So this is, of course, a problem that comes up in quite a lot of contexts in biology. One example that we'll be seeing, I guess, a few variants on is the question of energy minimization. We saw previously some examples of discrete models of minimizing the energy of a conformation of a molecule, like protein folding. But more often, this is something handled as a continuous optimization problem. We might assume that maybe we have some protein, we've got a set of atoms, bonds between them and so forth, and we're trying to find a minimum energy configuration of this protein. So maybe in a simple version of this model, we might allow just a few ways this can move, maybe just allow some side chains to rotate. In a really complicated version, we might allow independently every atom to have an X, Y, and Z coordinate, and we're trying to find the minimum energy configuration of the entire molecule as a function of all of the X, Y, and Z coordinates. In other cases, we might be talking about something like a docking problem. So in a docking problem, we might have, let's say, a large protein and a small molecule. We're trying to figure out how that molecule sits in a binding pocket of the protein. That might also be represented as an energy minimization, or maybe we've got an X, Y, and Z translation, and maybe a theta, phi, and psi set of rotation angles. We're trying to figure out the way to optimize these 6 angles describing position and orientation of the small molecule to minimize the energy of docking in a protein binding pocket. This, of course, comes up in many other kinds of problems in other domains of biology. So in phylogenetics, for example, we may have a phylogenetic tree we're trying to learn, and we might be interested in optimizing the lengths of the branches of the tree. So figuring out what relative lengths would best correspond with a set of data available to us. And likewise, this will come up in examples of, let's say, biological imaging. We may have an image, and we're trying to recognize some object on that image. And we can represent this as the problem of optimizing position and maybe orientation and size of a model of the object we're looking at relative to the actual image. And we'll see this towards the end of the class quite a bit in the context of model inference. So in many cases, we might be interested in learning properties of a model, let's say learning rate constants or some kind of reaction model where we're simulating some sort of reaction curves and we have real data we're trying to fit to these. Very often that kind of parameter inference or model learning problem will be represented as an optimization problem of trying to minimize deviation between the real data and the model as a function of the model parameters. So this is just to give some kind of motivation for what we're trying to do here and why we need to know about these things. Are there any questions about any of this yet? Okay, so when we talk about continuous optimization, we usually have to make some assumptions about what we're trying to do. So it's not as general in some sense as discrete optimization, where we can pretty much come up with any discrete problem and at least talk about how we would optimize globally over possible solutions to that problem. So with continuous optimization, we'll often have a few basic assumptions we work with. One of these is that we're usually going to assume that we are working with a continuous function. So it's not generally going to be possible to optimize for a function, or at least optimize except over finite regions if you have discontinuities in the function. And the theory behind how we do this will often make a significantly stronger assumption called C-infinity continuity. And C-infinity continuity essentially means that we don't just have a continuous function, but we also have a function for which every derivative of that function is continuous. So the first derivative, second derivative, etc. And it's a multivariate function that would be with respect to any combination of the variables, that all of those are continuous, at least on whatever region of interest we're looking at. In some cases, we'll have to go even further, and we'll need to say that whatever function we're optimizing, our energy, let's say, that all of the derivatives are bounded. So we would say that there's some bound on the absolute value of every derivative we're looking at. And some of the theory, and I'll try to point this out as we get to it, some of the theory will break down for some of these methods if you assume the derivatives can grow unbounded. Often, if you have really tight bounds on these, you can actually drop some of the assumptions I'll be telling you about and get better kinds of optimization. But generally, we'll assume there's some sort of upper bound on the derivatives. One other very important assumption we need to worry about with continuous optimization is that usually when we talk about optimization in the continuous case, we're talking about local rather than global optimization. So the distinction would be that if we're looking at some continuous function, we might have a potential surface, that is an energy or whatever we're trying to optimize for, that might look something like this. We're trying to find, in a global optimization case, specifically this point where the function goes to a minimum. But very often with a continuous optimization problem, the best you can really do is, if you're given some starting point, you can figure out the nearest local optimum. The nearest optimum you can get to where no infinitesimal changes in the parameters can improve on that. So this would be a global optimum. This would be a local optimum. And for the most part, what we'll be assuming here is we're actually covering techniques for local optimization. If you have guarantees like this, you can sometimes come up with ways to turn a local optimizer into a subroutine of a global optimizer. But we probably won't be covering that this year. But just be aware, you need fairly restrictive assumptions on your model in general to be able to do global optimization. Any questions about that? Okay. So that basically is what we're trying to do. And to explain how we do it, it helps, I think, to start with a simplification of the problem we're looking at. And that is to look initially at one-dimensional optimization. So initially, what we're going to assume is that we're finding either a minimum or a maximum of some function that I'll call capital F of a single scalar variable x. And so One of the key things that will help us do this, and that's really kind of central to many of the methods we'll use, is an observation that many of you have probably seen in your calculus classes before, and that is that if we have some function we're looking at, let's assume we're trying to do this on a closed interval, so we've got some x min and x max that we're looking at, then the maxima or minima of the function have to be at positions at which the derivative of the function is equal to 0 or be at the endpoints of the interval. So for a function like this, we would have a minimum that occurs here, specifically where this function has a value that is 0 in the derivative of the function. Now there's no guarantee that every 0 is going to be a global optimum or global maximum or global minimum within this region. So we might have another 0 over here, which is not a maximum, or well, it's local maximum, but not global maximum within this region. But basically, for the most part, you can turn the problem of optimizing continuous functions into the problem of finding zeros of those functions. So basically, if you can find zeros of your derivative, that's how you can find maxima and minima of your function. Does that make sense to everyone? Okay, so that then really will become the main tool we're going to use. So primarily what we're going to be trying to do is to find zeros of functions, and we'll just assume that those functions are the derivatives of the things we're actually trying to optimize. So I want to go through a few of the basic one-dimensional methods, and then we'll see how to generalize that to higher dimensions. And we'll start with a really simple classic method for this called the bisection method. And so the bisection method I can illustrate graphically relatively easily, and then we'll go through the code or pseudocode at least for it. So let's say we've got an interval in which we're trying to optimize. So we've got some value that we know is the smallest value it might be, x min, the largest value at which we might find the 0 of our function, x max. And if we plot our function here, which again would be the derivative of whatever function we're trying to optimize for, and I guess I'll just say for purposes of notation, I'll sometimes refer to this as f prime of x or just little f of x when we're talking about the derivative. So if we're trying to find zeros of little f of x, then if we have a closed interval and we know that at one endpoint of this interval the value of the function is negative, and at the other endpoint the value of the function is positive, then adding in the continuity constraint tells us that there has to be a 0 in between this endpoint and this endpoint. So it's less than 0 on one side, greater on the other, and continuous, it has to pass through 0 somewhere in between. Now there's no guarantee there's a unique 0. It could pass through 0 several times in between, but we do have a guarantee that there is at least one 0 on that interval. And that guarantee is pretty much the basis of the bisection method. So the idea behind the bisection method is simply to recursively partition this interval until we get close enough to a 0 or shrunk the interval enough that we've got a pretty good idea of the 0 we're looking for. And graphically it would proceed essentially as follows. We know there's a 0 between x min and x max, so we'll simply pick a point midway between those, and we'll say that this point hopefully will be closer to the 0, or at least narrow us in on where it is. But at this point, unless we happen to exactly land on the 0, either the function will be negative there or it will be positive there. So if the function is negative, as we see in this case, then it must be true that since we had a negative boundary and a positive boundary before, that one of the two sides here will also have a negative and a positive boundary. In this case, we have a negative boundary here, we have a positive boundary here. So we've now narrowed down the interval where the 0 could occur to the right half of the region we were originally looking at. We could do that again and say, since we know there must be a 0 in this interval, let's cut it in half and ask whether the left side of that interval or the right side of that interval is guaranteed to contain a 0. In this case, we can see that the value of the function at our new midpoint is positive, so that guarantees there has to be a 0 on the left half of the interval. Now, just as before, we're not guaranteeing that there isn't a zero on the regions we're ignoring here. So we're going to recurse on this region, but it certainly could have been possible that there were a bunch of zeros on this region, but there has to be at least one in this region. And we can pretty much just keep applying that logic. Split that region in half, we get a positive value, so we recurse on the left. Split that region in half, we get a negative value, so we recurse on the right, and keep zooming in until we get close enough so the interval we're left with is narrow enough that we feel we've zoomed in on the zero we're looking for. Yeah?
This is assuming we know the derivative of the function.
Yeah, so to use this, we do need to know the derivative of the function, or at least be able to evaluate the derivative. I will come to methods we can use later if we don't have a way of analytically evaluating the derivative. So if you just have a routine that computes capital F of x, there's still ways to work with that. Any other questions? Okay, so let's go through some pseudocode to see what I was actually describing here. So essentially what our method is going to do is the following. And I'm just going to make the pseudocode a little simpler than it would really have to be by assuming that we're in a case like this where the left endpoint is negative and the right endpoint is positive when we start out. So you just kind of need to flip all the signs if it's in the other case, but it'll just save me having to write everything twice. So basically what we're going to do is we're going to say we start with some xmin and xmax, and the first thing we're going to do is compute what we'll call fmin, which is simply f of xmin, and fmax, which is f of xmax. So those are the values of our function on the interval. And then we're going to repeatedly do the following steps. We're going to compute a midpoint, x mid, which is simply x min plus x max over 2, so simply midway along the interval. We're going to compute f mid, so the value of f at this new midpoint. And then we're going to ask whether f mid is greater than or less than 0. Of course, it might be exactly 0, but let's just say we'll test if it's greater than 0. If it's greater than 0, what should we do? Yes, if it's greater than 0, that's going to mean we're in the situation where we pick the midpoint and the function is above 0 there, so we want to recurse on the left half of the problem, which means that what we're going to do is replace the right endpoint, x max, with our new midpoint, and we're going to replace f max with f mid, so that corresponds to shifting the right interval to end at the midpoint. And otherwise, we're going to shift the left endpoint. So say x min gets x mid, f min gets f mid. And then we're simply going to go back to the repeat and do this again and again. That's going to shrink the interval. Now, for an iterative method like this, you have to have a stopping condition, something that tells you when to stop doing this. And the way we would do that is by putting, let's say, some kind of until statement on the repeat. And a typical test we would want to do in this case would be to say that we will repeat until x max minus x min is less than epsilon for some value epsilon. So in other words, we'll shrink until our interval gets below some value of epsilon that we consider close enough that x min and x max are basically the same within our error tolerance. So this is sometimes known as a forward error. And it's one way of measuring the error in your approximation after a certain number of rounds. We'll sometimes alternatively see what's referred to as the backward error. And the backward error would be just, let's say, the absolute value of f mid, testing whether that's less than epsilon. So we're trying to find a 0 of f, so we want f mid to be small. If you put your stopping condition to be a test on how large f mid is, it's simply an alternative way of deciding when you're close enough to a solution. Then whenever we decide to stop, all we need to do is return the final value we get, and we can say, let's return x min plus x max over 2. Guess as to where the 0 is. So does this make sense to everyone? Okay, so now that we've got the pseudocode here, I'd like to quickly walk through an example just to make sure we've got this down. And we take a very simple function here. Let's say we're trying to find a 0 of f of x equals x squared minus 2. So what should be the 0 of that, of the zeros? It'd be plus or minus square root of 2. And I'm going to assert that we will start with the interval x equals 0 to 2. So we'll be looking for the positive square root of 2, but we're going to assume we don't know that and try to use the bisection method to find that. So we're assuming we're looking on this interval from 0 to 2. So that would be on the x-axis. I'm going to assume that's 0, 1, 2, minus 1, minus 2. And our curve is going to look something like this. So at x equals 0, this is minus 2. At x equals 2, this is 4 minus 2, which is 2. So in other words, we've got the point 2 comma 2 here, and the point 0 comma minus 2, and then we're going to apply the bisection method. I find it often helps if you're trying to do this by hand to organize things into a sort of table. So we can say that there's some x min, let's say f min, x max, f max, and x mid, f mid, and then we can walk through a few rounds of what this would look like. So x min, we're given as 0, x max, we're given as 2. I've already told you that f min is minus 2, f max is plus 2. And then what we would want to do is find x mid and f mid. So can anyone tell me what x mid should be? Yeah, that should be 1. And then what would f mid be? It would be minus 1, so 1 squared minus 2. So then in the next round, this would be equivalent to taking a point about there. What would we do next? What would x min be in the next round?
1.
Yes, we're going to copy these values up to here. So we get a 1 minus 1 here. We're going to keep x max and f max where they were. And then what would x mid be in the second round? Yeah, midway between 1 and 2. So that's 1.5. If we plug in here, 1.5 squared is 2.25 minus 2. So that's 0.25. So then what would x min and f min be in the third round? Yeah, we're just going to keep them the same as they were. So essentially, we picked a point that is just to the right of the 0 here. We're going to copy these values into x max and f max. And then we would pick another midpoint that's going to be 1.25. If we plug that into the formula, it's going to come out to about minus 0.44. And basically, we could keep going like that. But this would, over successive rounds, get us gradually closer and closer to the square root of 2. Does this make sense to everyone? Okay, so when working with a method like this, we're often interested in the question of how quickly does it converge? So this kind of algorithm we analyze a little differently than you would typically do with a discrete algorithm, but we can think of convergence as a function of whatever epsilon we're looking at, and also, of course, be a function of the size of the interval we start with. But in the general case, how would the number of rounds of optimization we need depend on epsilon? Asymptotically, what would the number of rounds of optimization be? It's going to be on the order of the log of epsilon inverse. So basically, the smaller you make epsilon, the more rounds you need, but the number of rounds is going to grow logarithmically with epsilon inverse. So making epsilon half as small means you need one more around it. Does that make sense to everyone? You might think that that would be a pretty good runtime, but you can actually do significantly better. We'll get to that a bit later, but that's the performance of this method. Now, before we get to a much better method for this problem, I want you to talk about a slightly better method that I think you wouldn't usually want to use, but it helps illustrate the much better method I want to get to a bit later. And the slightly better method is based on the idea of taking the bisection method and trying to accelerate it a little bit. So let's say we are trying to do bisection. We've got our 0 axis here. And let's say for the sake of argument, we're looking at an interval here. We take our midpoint. We see that maybe we've got a value of the function that's negative here, so we want to recurse on this right interval here. And then we want to pick a new midpoint. Now, this new method I want to tell you about tries to do something a little bit more intelligent than what the bisection method does. What it tries to do is say that we can observe that the absolute value of this is relatively small, so the distance from 0, whereas the absolute value at the other endpoint of the interval is much larger. So if we assume our function is reasonably well-behaved, and well-behaved usually means something like close to linear, then probably the 0 is closer to this endpoint than it is to this endpoint. We could just kind of guess the 0 is likely to be shifted away from the middle towards the endpoint that has a small absolute value of f rather than the one with a large absolute value of f. So that is something we can take advantage of in principle to try to improve the bisection method. And the idea behind it is to do something that's known as locally linearizing our function. So essentially pretending our function is linear within the region we're looking at. And we would do this by saying that we know one point on the function, we know another point on the function. So if the function were linear, it would look something like this. And what we're going to do is pretend that that's actually the case and use that linear model to try to project where the 0 is. And then instead of putting our new midpoint directly in the middle of the interval, we'll try to put it where we think the 0 is, on the theory that that's going to zoom in more quickly on the actual 0. So that is the basis of a method called the secant method. And what we're going to want to do is see how you would do that. So how would you modify the bisection method to turn it into the secant method that uses this local approximation? Well, to do that, the first thing we're going to need to do is figure out how to express or provide a formula for this line that passes between the two endpoints we know about. So if you remember back to your algebra you may have taken in high school or middle school or whatever, one way of expressing a general formula for a line is to take a point on the line, x0, y0, and then you can express it as y minus y0 equals the slope, which might be y1 minus y0 over xy minus x0 for another point x1, y1 times x minus x0. So in other words, if this point for x0, y0, and this point for x1, y1, then this thing, y minus y0 equals y1 minus y0 over x1 minus x0, x minus x0 is a general formula for the line that passes through these 2 points. Does this sound familiar to everyone? Okay, so in this case, if we plug in the values we have, we've called this x min f min, this one x max f max. So what we're trying to assert here is that we're trying to find the 0 of a line described by f of x minus f min equals f max minus f min over x max minus x min. So in other words, the slope times x minus x min. So this is going to be the general formula for the line we're interested in. And we're trying to find where this f of x goes to 0. So we're trying to find the value of x that would make f of x 0. So if we want to do that, what we would do is take this general formula for the line, where we're now pretending our function is linear, express it in terms of f of x. So In other words, f of x equals f min plus f max minus f min over x max minus x min, x minus x min. And we're asserting that we're looking for the point where that's 0. And then we just need to solve for x, and that would tell us where that line goes through 0. Does this make sense to everyone so far? Okay, so we have an equation here. We want to solve that equation for x. We can do a little rearrangement, so move the f min to this side, divide by the slope, add x min. And what we'll get out after we do all of that math is the following. X equals x min minus x max minus x min over f max minus f min times f min. And what that's telling us is that this is the value of x we should use to figure out where that line goes to 0. And we can essentially take this and just plug this in for this line here, where we calculate x mid in our formula for the bisection method. So just replace this with x mid, and we now have the secant method. That's really the only difference you have to make. So just a slightly better, or usually better, way of picking the midpoint of the interval, and that one substitution turns the bisection method into the secant method. So does that make sense to everyone? Okay, so we can see how this would work taking the same example we had before. So we're looking between 0 and 2. We're trying to find the 0 of f of x equals x squared minus 2. We know that has an intercept of 0 minus 2, has an intercept of 2, 2. And with the secant method, we can walk through the steps. I'm not going to bother writing the table. I think there's an example in the text if you want to see that. But basically, we would start out the same. We would observe that we've got a point at 0 minus 2. That's our left end point. We've got a point at 2, 2. We would pick the midpoint implied by the secant line. And in this case, it would actually end up, for the first round, doing exactly the same thing as the bisection method. If we look for a line passing from 0 minus 2 to 2, 2, that line is going to pass through the point 1, 0. So that would be our next guess for x, that x is 1. We would evaluate f there. That would drop us down to this value here, which would actually be 1 minus 1, because this isn't actually a linear function. We would then recurse on the right interval here. So we now have as our left endpoint 1 minus 1, our right endpoint 2, 2. We would project a line between those 2 points, see where that goes to 0. In this case, that's going to end up being at 1 1/3 and about minus 0.2 when we drop it down here. We're going to project a line through there. Going to see where that goes to 0, and so forth. And that basically is the difference between the secant method and the bisection method. So in this case, it's going to end up converging somewhat faster on this example. Asymptotically, it isn't necessarily better. It tends to do better in practice, but it more or less has the same kind of what we call geometric convergence as the bisection method. On average, it gets better by about a constant fraction on each round of operation. So it still have a performance. Typically, that's something like the log of epsilon inverse. So I don't want to dwell on this method because, as I say, it's not usually the thing you would really want to use for problems like this, but it illustrates an interesting point that I'll get back to in a second. Before I move on, though, are there any questions about the secant or bisection methods? Okay, so the basic idea behind the secant method is this notion that if we can take our function and kind of pretend it's linear, we can use that to get a good idea of where the next 0 of the function is going to be. And that is also the intuition behind this somewhat better method that I've been alluding to. But this better method takes that a bit further, and it says that we'll look at our curve that we're trying to optimize. Look at the curve where we're trying to find the zero, so maybe this is the zero axis. And instead of taking 2 points and trying to pretend that the curve is linear between those 2 points, what we're going to do is try to take the limit as we move those 2 points together. So in other words, instead of pretending we have an interval that we know about, we're just going to pretend that we've got one guess as to a good point on the curve, and then we're going to try to linearize the function in the immediate vicinity of that point. So in other words, we're going to put a tangent to our function at that point. So try to find a line that matches the slope of the function at that point and matches the value of the point at that point. And just like in the secant method, use that to try to get a guess as to where the zero is, and then repeat from there. So we would move to the point that we projected was the zero. If the function isn't linear, it probably won't be exactly the zero, but we can then reevaluate the function there, project another tangent, see where that hits, move back to the curve, project another tangent, and so forth. And the idea is that this will give us something sort of like the secant method, where we can start with an initial guess and then keep refining that by using that guess and the slope of the curve to project where our zero should be and get a better guess. So is the high-level idea at least clear to everyone? Okay, so what we want then is something kind of like what we want with the secant method. We want to find a way of taking our curve f of x, pretending it's linear in the vicinity of some current guess, let's call it x0, and use that line passing through x0 to find a projection to a next step, x1, which would be our next guess, and then use that to go to x2, and so forth. So we can use a slightly different formula for the line than before, and say that in the general case, if we've got a point x0, y0, and we know the slope of the line, let's call it m, then an equation for the line passing through point x0, y0 with slope m is going to be y minus y0 equals m, x minus x0. We're going to need m, though, and we no longer can assume we have 2 points to use to project m. So how would you figure out what the slope of a line is from a single point on that line, or the slope of a curve? Yeah, you take the derivative. So what we're going to want for m here is simply f prime at x0. So in other words, what we're going to do is pretend our function f is linear by looking for a solution to f of x minus f of x0 equals f prime of x0, x minus x0, and try to solve for the x that will make f of x equal to 0. Just like when we did this with the secant method, what we can do is rearrange, put that in the form f of x equals f of x0 plus f prime of x0, x minus x0. Say that we're trying to figure out where that is equal to 0, and then solve for x to get the projection of that tangent line to the value f equals 0. So in other words, we're taking this thing equals 0, we're solving for x. If we rearrange, what we're going to get is the following. So we're going to move the f of x0 to the right-hand side. We'll get f prime of x0, x minus x0 equals minus f of x0, divide through by f of x0 to get x minus x0 is minus f of x0 over f prime of x0, and then finally x equals x0 minus f of x0 over f prime of x0. And that would tell us if we have an initial guess, x0, then our next improved guess would be the x given by this formula. So this is pretty much the entirety of a usually better algorithm for zero finding that is known as the Newton-Raphson method. So you'll sometimes see this referred to as just Newton's method, and I'll just repeat what I was told when I learned about this. So Newton really doesn't need the credit, but when else are you ever going to hear about Raxon? So let's just give Raxon the credit he deserves and call this that's second order accurate in delta x. So for small delta x, this would be expected to be a significantly more accurate approximation than this one. Now we could derive other orders of accuracy by simply taking whatever combinations of perturbations of f of x we want. So we could take f of x plus delta x, f of x minus delta x, f of x plus 2 delta x, f of x plus 3 delta x, whatever mixture of these we want. And what we do to derive a formula like this is basically convert it into a linear system. We're trying to take some multiple a of this term, some multiple b of this term, such that a times f of x plus b times f of x is 0, so we cancel out that. A times delta x f prime of x plus b times delta x f prime of x equals f prime of x. A times delta x squared over 2 f double prime of x plus b times delta x squared 2 f double prime of x is 0, and so forth. Just put together your Taylor expansion, set up a linear system to cancel out as many of the terms as you don't want as possible, and then you get whatever order of accuracy you want out of this. Does that make sense to everyone? Okay, so this is basically how we would handle these kinds of problems if we don't have a way of analytically computing the derivative, or if the analytical derivative is simply too messy to deal with. You do have to be a little careful, though, because you might assume you could take an approximation like this, and if the error is proportional to delta x, then you can just make delta x really small, and you'll get a perfectly accurate approximation. So what would go wrong with that? Why can't we just make delta x infinitely small?
It's a floating point, and dividing by floating points probably has some loss of precision.
Yeah, so you're going to lose precision dividing by a small number, and you also lose a lot of precision if you subtract two very similar numbers. So if delta x is really small, f of x plus delta x will be very close to f of x, and you lose all your precision if you have a finite approximation and you're subtracting two very similar numbers. So basically you kind of have to balance this. If you know what your machine precision is, you don't want delta x to be smaller than about maybe the square root of the machine precision. So that's really why we would want to use often a higher order accuracy approximation rather than just sticking with the simpler one and going with a very small delta x. There are practical limits on how small delta x can be. All right, so any questions about any of that? Okay, so that pretty much gets us through the question of optimization of functions of one variable. But usually what we're going to want to deal with are more complicated kinds of optimizations where we're looking at a function of many variables. So in this case, we're looking at an optimization with respect to maybe two rate constants. Here we might be looking at an optimization with respect to potentially thousands of different coordinates of different atoms. And so we need a way of dealing with that case. So it happens that the Newton-Raphson method at least generalizes to this kind of situation. There are more complicated ways of generalizing the secant or bisection methods, but I'll start with the Newton-Raphson method, and then we'll also see some alternatives to that. But before we can get there, we at least have to describe what problem we're trying to solve when we take a system where we've got a function of, let's say, n variables, and we're trying to figure out what the maxima or minima of that function are. So there's an analog to the one-dimensional case, and that analog says that just as in the one-dimensional case, a minimum or maximum of f of x occurs where f prime of x is equal to 0. In the multidimensional case, what we have is an assertion that the minima or maxima of a multidimensional function, so minima or maxima of f of a vector x, could be this f of x1 through xn, occur at places where all of the partial derivatives with respect to each of the x's are 0. So where maxima and minima of this occur, it must be the case, unless we're at the end point of a finite interval, it must be the case that the partial derivative of f with respect to x1 is equal to 0, partial derivative of f with respect to x2 is 0, etc., up to the partial derivative of f with respect to xn is equal to 0. So if there's some vector x where that occurs, that is a potential maximum or minimum of our function. So does anyone know what the vector of all of these first partial derivatives is called? So that is known as the gradient of f. So the gradient of f is just the vector of all of the partial derivatives of f with respect to each of the variables, and we'll often abbreviate that by this triangle. So what we're really asserting here is that maxima and minima occur at points where delta f is the all zeros vector. Gradient of f is the all zeros vector. So that makes sense to everyone? Okay, so we can see a little example of this. So let's suppose we are looking at a system where maybe we've got two pieces of a protein coming together, and there is an ion kind of on a long tether, so a long molecule that sort of links it to the protein. And there is, let's say, some positive charge here, and we'll suppose the ion is negatively charged. We want to figure out where this ion will sit in this pocket within the protein. And we're going to come up with a model where we're going to assume that this molecular tether we can model as if it were a spring. So you kind of imagine there's a spring pulling this ion back to this protein, but we also have this charge force pulling these two charges together. And that might be a case where we would try to figure out where the energy goes to a minimum. So where would this piece be positioned to minimize these counterbalancing forces? So to figure that out, we might say we've got a function, and I'll just propose it as a function of two variables. So assume we're looking at a two-dimensional case here, x and y, where we might have some spring force. Let's say that the spring force has some spring constant k, and we've got some deviation of x from this anchor point, 1, 1, and some deviation of y from that point. And that would be the potential energy contributed by the spring at a deviation xy. And we would have some charge force, which let's say is r over x squared, square root x squared plus y squared. So that would be the charge force if we were moving these two ions, keeping them a separation of xy from one another. So is the example clear to everyone? Okay, so if we wanted to find maxima or minima of this function, then what we would want to do, first of all, is find the gradient. So the gradient of f is equal to the partial derivative of f with respect to x, and the partial derivative of f with respect to y. In this case, that will come out to, first of all, taking the derivative of this term with respect to x, which is going to be k x minus 1, and then adding in the derivative of this thing with respect to x, which will be rx over x squared plus y squared to 3 halves. And that is going to be the partial derivative of f with respect to x. And then the y term will be symmetric. So y minus 1 plus ry over x squared plus y squared to 3 halves. And then the assertion of this theorem is that we have to find x and y that makes both of these things 0, and that will be a possible maximum or minimum of this function. So is that clear to everyone? Have any questions about that? Okay. So we don't quite have what we need yet to do the Newton-Raphson method. So this is going to be equivalent to taking our original function we're trying to optimize. So that is f of x. Turning that into the function we want to find the 0 of, we would say is little f of x. But to solve the Newton-Raphson method, we need both little f of x and the derivative of that little f prime of x, which is the second derivative of the thing we're trying to optimize. So with Newton-Raphson, you're working with the first and second derivative of the thing you're trying to optimize, because this is the thing you're trying to find the zero of. So we need, essentially, this thing, the gradient is equivalent to this. This is equivalent to this, and we need the thing that's equivalent to this. This thing, so the thing equivalent to the second derivative of our multivariate function, is known as the Jacobian of the gradient, or more commonly as the Hessian of f. And the Hessian is simply a matrix. And just as the gradient is a vector of the first partial derivatives, the Hessian is a matrix of the second partial derivatives. So in other words, if we are doing a two-variable equation, the Hessian, call that h, is going to be equal to the second partial derivative of f with respect to x, second partial derivative of f with respect to x and y, second partial derivative of f with respect to x and y again. So these two terms will be symmetric. In general, this will be a symmetric matrix. And second partial derivative with respect to y. So that's the Hessian matrix. And this thing is the equivalent of the derivative. In this case, Hessian starts to get a bit messy. Very often that's going to happen in these problems. But let's say we just continue with that gradient from before, and we can say the Hessian of x and y is going to be, first of all, second derivative of f with respect to x, which is simply the first derivative of this thing with respect to x. Just write down what that comes out to, because as I say, it gets a little messy. That will come out to k, so first derivative of kx minus 1 with respect to x is k, plus then the messy part, r x squared plus y squared to the 3/2 minus 3r x squared, square root of x squared plus y squared, over x squared plus y squared cubed. That's going to be second derivative with respect to x. The partial with respect to x and y is going to come out to 3r xy over x squared plus y squared to the 3/2. This will also be 3r xy over x squared plus y squared to the 3/2. And this term here will be symmetric to this one here. Just swap x and y. It'll come out to k plus r x squared plus y squared to the 3/2 minus 3ry squared, square root x squared plus y squared over x squared plus y squared cubed. Does that make sense to everyone? All right, so those give us the basic pieces, the analogs to the terms we had for the one-dimensional Newton-Raphson. And we just need to generalize the formula, the iterative formula. So before we had xi plus 1 gets xi minus f of xi over f prime of xi. In the multidimensional case, we would have a vector xi plus 1, and that would be simply vector xi, so our previous vector of values. And then we need to do an analog of f of xi, so that's going to be the gradient of f at xi, and an analog of dividing by f prime of xi. So we can't divide by a matrix. So what do we do instead?
Take the inverse?
Yeah, so we're going to take h inverse at xi times the gradient, subtract just like in this formula, and this is the multi-dimensional Newton-Raphson iterator. So is that clear to everyone? Now you might notice that things get quite messy in computing the Hessian. You can actually use the same techniques I was talking about before to get around the problem of explicitly computing the Hessian. So use the numerical approximations to the derivatives, for example. So you might analytically compute the gradient, and then use forward difference approximations to estimate the terms of the Hessian from the gradient. That may be easier than explicitly computing the Hessian. But basically, once you get to this point, things are not too much more complicated than with the one-dimensional Newton-Raphson. There are a few practical implementation things to be aware of. One of them is that you usually don't want to explicitly compute a matrix inverse. So if we don't want to compute the matrix inverse, can anyone think of what we could do instead? How could we figure this term out? We're trying to find some value, let's call it yi, that is equal to this thing. So if we assert that yi is equal to h inverse delta f, then that's equivalent to saying that h yi is equal to delta f. What's that?
The eigenvalue?
Well, not the eigenvalue, but at least a linear system solution. What we've got here is a linear system. We know h, we know the gradient, we're solving for y. We can just plug into any of our linear system solving algorithms, and that will give us a solution to our problem. So that's usually what we would really do rather than trying to invert the Hessian. All right, so any questions about any of that? Okay, so that gives us one class of methods that we can use, and this Newton-Raphson method, just like in the case of a one-dimensional problem, tends to be very fast if we have a good enough initial guess. Once you get close to your zero, it converges very quickly, but it tends not to be such a robust method. If you're not too close to the guess, it can actually make things worse, so it can just fly off into infinity. So often you want something that's a bit more robust to work with. And we actually have most of the tools to a much more robust method that is known as the steepest descent or gradient descent method. And the idea behind steepest descent is that it uses an observation about the gradient, which is that if we take any function, and let me draw a contour plot that expresses values of, say, regions in the xy plane of constant value of some function f, then there's a property of the gradient which says that at any point on the function, the gradient points in the direction of steepest descent. So in other words, the direction in which the function falls as rapidly as possible. And the idea behind the steepest descent method is that we can use that to come up with a more robust sort of optimizer. Basically take some value on the function where we can evaluate f of xy and move in the direction of the gradient and keep moving until we get to some optimal point along that line, and then pick a new direction, move along that, pick a new direction, move along that, and that gives us a way of getting relatively quickly to an optimum of our system. So that is known as the steepest descent method. And the algorithm is not too complicated once we know how to compute a gradient. Essentially, what we're trying to do here is take some initial guess, say xi, and we're trying to assert that there is some improvement of that, a distance r along the gradient. So asserting that if we have xi, that we can improve on it by moving some unknown distance r along the gradient. In particular, what we're trying to do is find what's called the argmin over r of f of this thing. So in other words, we're trying to find the value of r that minimizes this function. And that would tell us the optimal point along that line for minimizing the function. So can anyone think of how we could solve this? How could you find r? Well, this is just a one-dimensional optimization. We've converted our multi-dimensional optimization into an optimization of just a single variable r, so we can use any single variable optimizer. We can use bisection or whatever, find the best value of r, and then this becomes xi plus 1 gets xi minus r gradient of f of xi. That gives us our next guess, and we simply repeat until some stopping condition. So that basically is the steepest descent method, and this tends to be a much more robust method than the Newton-Raphson method. So robust in the sense that even if you've got kind of a poorly behaved of your function. There's an even more sophisticated method I'll just mention briefly called the Levenberg-Marquardt method. And Levenberg-Marquardt is basically a way to try to get the best of both of these methods. Try to get the best of this Newton-Raphson method and the steepest descent method, and do that by observing the following. If we take the Newton-Raphson iterator, xi plus 1 gets xi minus Hessian inverse gradient, and we compare that to the steepest descent iterator, xi plus 1 gets xi minus, let's just say, r times delta f, or gradient of f, we can observe that this thing r can be replaced with some scalar lambda times an identity matrix. We're just multiplying the gradient by a scalar, inverse delta f, and then we put these into an almost identical format. And the assertion behind the Levenberg-Marquardt method is that we can make a better method by combining these two things, saying that xi plus 1 gets xi minus the Hessian inverse, or excuse me, the Hessian plus lambda I inverse delta f, and then just adjust lambda. If lambda is really small, this term goes away. This becomes just Newton-Raphson. If lambda is really big, this term dominates, and it's equivalent to having a very small r. So essentially, when you're far from a solution, the method isn't working so well, make your lambda big. This turns into steepest descent, and the bigger it is, the smaller the steps you take along your gradient. When you get close to a solution, you shrink your lambda, it turns into Newton-Raphson and converges very rapidly. So that basically is Levenberg-Marquardt. It's an example of what's called an adaptive method, where by looking at how well the method is working, you can tune a parameter and make it shift between a kind of method that works well far from zeros and a kind of method that works well close to zeros. So I know we are about out of time here. I'll just briefly mention one minor improvement of this, that often instead of using the identity matrix, you would actually substitute the diagonal of the Hessian. That tends to improve things, but basically this is pretty much what people tend to do for hard optimization problems like this. This is probably the most standard method for solving hard multidimensional optimizations. All right, so I think we are out of time. Are there any last questions before we break? Okay, I'll see you all on Thursday.